Okay, so thanks to the organizers for a great conference at a great location. I'll talk about some ongoing work with Amit and Sunny. And so let me start with some generalities just to get us in the mood. So of course, in quantum field theory in general, we think about it, at least in situations where it's mathematically well-defined, as some RG flow between a UV fixed point and an IR fixed point, which may or may not be non-trivial. And if we want to be precise, we have to start with CFT in the UV and then specify a certain finite number of coefficients of relevant and marginal operators that describe the particular RG trajectory that we're interested in. And this is, of course, what's known as flowing down the renormalization group. Now, if you ask what a certain RG trajectory looks like from the perspective of the infrared theory, it looks like a perturbation of the infrared fixed point by a set of irrelevant operators. But the situation is very asymmetric, because if we specify a certain finite number of irrelevant deformations of the IR fixed point, we are not really dealing with a well-defined QFT, essentially because there's an infinite number of different RG trajectories that end up at the same place. This is basically what's known as irreversibility of RG flow. And all this stuff has a simple analog when we talk about holography, which has to do with the fact that the original fixed point, say a UV fixed point, is described by a AdS space-time. If we perturb it by relevant and marginal operators, we're basically preserving the AdS asymptotics, and it's easy to see that there's a finite number of parameters that we can turn on. But if we're turning on irrelevant operators in the dual CFT, then there is essentially an infinite number of parameters that we need to specify to tell what the new geometry is in the UV, and that obviously is the dual of this previous thing I said. Now, what I want to do in this talk is talk about a variation of this theme, which came to my attention in these two papers that were mentioned yesterday by Smirnovitz and Molochikov and an Italian group, who talked about a situation that where it sort of is not supposed to happen, a two-dimensional conformal field theory deformed by some irrelevant operator that is much better behaved, supposedly, than the general case that I just described here. And moreover, in a certain sense that I'll mention in a moment, is solvable. So I'll talk about the results briefly, and my main focus here is going to be about the holographic analog of what these people did. The main interest our main interest in all of this was because both in this work and in its holographic dual, we're dealing with a situation where in the infrared we have a two-dimensional conformal field theory, while in the UV we have a Hagedorn density of states. And so if we can really bootstrap our way to understanding how holography works in these situations, like flat space-time, that would be a useful step in the study of holography. So let me start by telling you or reminding you, if you know this already, what these people did. So they said, let's take any conformal field theory and add to the Lagrangian an operator that at first, when you add it, looks like the product of the holomorphic and anti-holomorphic stress tensors. Now, of course, this operator has dimension 4, and so the coupling that I call little t here has units of length squared. It's a scale, so at distances much larger than the square root of this t, you basically have the original CFT, and then as you flow up the RG, you, as I said earlier, expect the story to break down at distances of the order of square root of this t. But in fact, it doesn't seem to do that. More precisely, what these people claimed is that if at a generic point along the RG, you define the deformation in this way that I indicate there, where theta is the trace of the stress tensor at that point in coupling space, then not only does it not break down, you can actually compute exactly the energies of states in the massive theory. To be more precise, you can answer the question, what happens to the energies of the states in the original infrared theory when you turn on T? As I'll mention in a second, this is not necessarily the most general thing. So here is what the formula that they get. If you start with some theory with central charge C, and you look at a state which has L0 equals L0 bar equals some number H. For concreteness, I took them to be the same, the values of L0 and L0 bar. Then we know very well that in conformal field theory, the formula for the energy is this thing written here. Here actually R is the circumference. This is their notation. And this formula is deformed into something like this with a square root, which they claim is an exact result independent of the UV completion sort of this story. So in any reasonable UV completion, they say that the state in the original CFT with this energy goes here. And of course, you know, I chose to write the formula for equal L0 and 0 bar, but there's a similar looking formula for the general case. Now, if you looked at states with H larger than C over 24 in the original theory, which, for example, is what you would get if you were dealing with a supersymmetric theory with supersymmetry preserving boundary conditions on the circle, what you get there is some picture like this. If the original energy was much, much smaller than the inverse of the coupling, this T over R squared you can think of as just the value of the coupling T at the scale R, then the formula says that the exact energy is more or less the same as the original one, so such states are not really influenced much by the perturbation. But on the other hand, if you start with a large value of the original energy, larger than 1 over the coupling, then the energy formula gets deformed a lot. And the crossover between the two regimes is basically where the dimensionless energy, E times R, is of the order of 1 over the coupling. So that's what they get, these people. And one aspect of what they get that I want to stress is the entropy. So you can ask how many states are there. Now, it's important to stress, especially because of all this general stuff I mentioned before about flowing up the RG, is that we can't really answer the question of what is the entropy of this theory. All we can say is what is the entropy of the states that we can identify in the low energy CFT. It could be, for example, that in the exact theory there are some states whose energies go like this scale I was mentioning before that decouple in the infrared limit, and then you would never see them in, you know, like they're not described by this formula because they're just not there in the infrared. However, if we calculate the entropy of the states that we do see in the infrared, we get a lower bound on the entropy. And what this lower bound looks like is like this. So at the energies below this crossover, we get just two-dimensional conformal field theory entropy. And then when we go to higher energies, we get the Hagedorn entropy with a certain value of the Hagedorn temperature that's associated with this coupling T. So that's interesting. This is a situation where if you indeed can make sense out of this RG flow, we get to push our way from a field theoretic entropy to Hagedorn entropy sort of without losing any predictive power. I mean, that's the maximally optimistic scenario. However, as I said before, there are some issues. Other states, for example, that decouple when you go to the infrared limit, etc. Now, with these issues in mind, what I want to ask is what happens when you embed a story like this in the context of holography. And so if I deal with a CFT that has an AdS dual, can we do something in the AdS dual that will be like what I just described? So let me say a few words about that. So of course, we could just do literally what I just said, namely construct the stress tensor of the CFT in the AdS. We know how to do that. The stress tensor is a single trace operator, and so TT bar is a double trace deformation, which basically is described by changing the boundary conditions for bulk fields in AdS. And I actually am not going to pursue this direction here for various reasons that will become clear soon. What I'll show instead is that there is an interesting single trace deformation that we're actually very interested in that shares many elements with this discussion that I just finished. Let me say something about that. We're looking for something universal, right? So the story that I just told you is universal in the sense that for any two-dimensional conformal field theory, you have this operator, TT bar, that you can run this program with. And so the question is there something similar in string theory on AdS space? I'll concretely be talking about AdS space supported by Navier-Schwarz B field. And the answer is that yes, there is such a thing. There is some operator that I will say a few words about called D of X, that I will call D of X, that I constructed with Zyberg in 1999, which is very similar to this TT bar thing. So it's just a perturbative string excitation. It's quasi-primary of the space-time Virasoro, has the same OPE you can show with a space-time stress tensor as this TT bar guy. And so we can ask what happens when we perturb the CFT2 with that operator. Now, I don't want to talk about the construction of this operator in detail. I put on this transparency some formulas that for people that are familiar with string theory and AdS3 will say something, for others probably not, but you can look them up if you're really interested. Basically, there is a SL2R current algebra. You can construct some natural currents that are labeled by a boundary position and a position on the world sheet. For reference, the stress tensor is described by some object like this, where phi1 is some bulk to boundary propagator. And this D, so this stress tensor has dimension 2, 0 in space-time. And this D operator, which as I mentioned has dimension 2, 2, looks on one side like the stress tensor T, one side on the world sheet, and with the other world sheet chirality, it looks like T bar. So, however, it's not T times T bar, it's a sort of a single trace or single string vertex operator. And it's essentially the massive dilaton on AdS3. And so you can ask what happens if you add to the Lagrangian of the space-time CFT this operator. Now, this operator is a supergravity field, so you know exactly how to deal with it. You can show that what it corresponds to from the world sheet point of view is some current perturbation of the world sheet theory. And one already interesting thing is that while the space-time operator is irrelevant, the world sheet perturbation that corresponds to it is actually marginal. And so you would think that it's much better behaved than the naive picture would suggest. And that's something that sort of is reminiscent of the work of these people from last summer that I mentioned in the beginning. And of course, being a current deformation, we actually expect it to be exactly solvable. So let me say a few words about this theory. So one comment about this deformation is that one of the reasons why, one of the simplest ways to see that it's exactly solvable is to think about it as a Coset theory on the world sheet. So the way you do that is you start in sort of 10 plus 2 dimensions. So you have AdS3. Let's say for concreteness, you're dealing with the kind of simplest example of AdS3 CFT2 correspondence, which is, 5 branes and strings in wrapping some flat spaces. And what you can do is add an extra 1 + 1 dimensional flat space, R11, which is I'm going to take to be parameterized by these light cone coordinates x plus and x minus. The AdS3 I will take to be parameterized by Poincaré. So gamma and gamma bar are coordinates on the boundary of AdS3. And when you take this 10 + 2 dimensional geometry, and then you do gauging, which is the same thing as Coset, by U1 squared. So alpha and alpha bar are the gauge parameters of the Coset, and you gauge, this is like a null shift of x minus and gamma, where the parameter epsilon basically mixes the R11 and the boundary of AdS3. So, so this is sort of a two-dimensional gauge theory on the worldsheet, and you can easily, using sort of all the techniques, calculate the background that this gives rise to. So you start with the original. So when A and A bar, the gauge fields on the worldsheet are 0, you have that background I mentioned, which is AdS3 times R11. You introduce the gauge fields that are associated with those symmetries. You solve for the gauge fields, and you get a background which looks like this, with some non-trivial dilaton. And if you just stare at it, it's clear that what it does is it interpolates between AdS3 when the radial coordinate phi goes to -infinity, and our sort of a line with linear dilaton times R11 when you go towards the boundary. Now, so this is what this deformation does, this current deformation. And it's actually something that we know very well, this background. This background where you take that three-dimensional geometry I had on the previous slide and tensor it with S3 and T4, which were just spectators in the story, is the geometry of strings and five-branes, where we're always in the near horizon of the string, of the five-branes, and we interpolate between also being in the near horizon of the strings at phi going to -infinity and being outside of the near horizon region of the strings and in the near horizon of the five-branes at phi goes to +infinity. So in words, what this deformation of the space-time theory does for us is it takes us out of the near horizon region of the strings. And that's actually something, I'm not going to have anything to say about this, but it's something that is conceptually interesting. We would be interested in many other situations to have the ability to control perturbations that take us out of the near horizon geometry of various branes and retain the good properties of the description. And this epsilon that appeared in the gauging is basically just setting the scale at which this happens. Now, you can ask, what is the spectrum of this thing, of this deformed theory, the spectrum of string theory on this space? And I don't want to go through a lot of details, but basically what you find is a continuum of states labeled by momentum and winding around that circle that we have on the boundary. And if you have excitation levels for left and right moving on the movers on the worldsheet, what I call here delta and delta bar, and this J is the mode that is the quantum number corresponding to the momentum in the radial direction, you get an energy that looks like this. So the usual momentum and winding contributions plus this factor. And then you also remember that if you look at this combination, it's actually exactly, according to some work of Maldacena and Oguri from 2000, if you go back to the undeformed theory, this combination that we had there is related to the values of L0 and L0 bar for those states corresponding to long strings on AdS3. So you put all of this together, like this mass shell formula, the value of J, and the the relation to the scaling dimensions. And what you find is an equation that looks like this, where I also shifted the energy to remind myself. Well, I guess I put the winding number to 1, and what I called the energy before, I wrote as energy plus the winding contribution, the energy sort of above the BPS limit. And interestingly, this formula is the same as the spectrum for the energies that I had before on one of the slides of a CFT with central charge 6K, deformed via this TT bar deformation with some particular value of the coupling that I did not put on this transparency. So in other words, for these wound strings with winding 1, what we get is that the supergravity deformation that I discussed here acts as a TT bar deformation of the sort that these people studied last summer. And this story persists for winding larger than 1, where you get sort of states in the ZW twisted sector of m to the w modest w, where m is just the theory of one string. Now, then you can think about black holes. So basically, there's this picture that is familiar from years ago, where if you take these long strings and you push them to higher and higher energies, so they push their way towards the boundary, where the coupling increases, you can show. This was shown by Zyberg and Witten in '99. And eventually they will become black holes. This is a picture that some people in Jerusalem and me discussed in 2005. And so you would expect, because of the fact that the entropy of perturbative strings that you get agrees, as I just said, with some kind of symmetric product structure, the same should be true for black holes. And this is indeed the case. So I guess in the remaining few minutes, I'll just say a couple of words about that. So basically the idea is on the field theory side, if you know, by field theory I mean you have a CFT with central charge 6K, the theory of a long string. You take the symmetric product of P of those things, and you ask what is the entropy as a function of energy. So the best thing you can do for yourself is distribute the energy equally between the P factors. And so what you need to do is calculate the entropy for one of those factors at energy epsilon over P and then multiply by P. Now, the entropy of each of those factors, I didn't write it down when I reviewed the results of those two papers, but it's very easy to calculate it. And what you get is something like this. On the other hand, the bulk calculation involves taking that geometry, this M3 cross, let's say S3 cross T4 geometry, constructing a black hole in it. So there's some formulae, but it doesn't really matter what the exact details are, and calculating its Bekenstein-Hawking entropy. I mean, it's clear that in the two limits where the energy is low and the energy is high, you will reproduce the, the Cardi entropy and the Hagedorn entropy just because of what the geometry does, because the geometry is ATS3 at sort of one region and linear dilaton in the other. But the question is, how does the interpolation go? And this is where you need the exact formula. And what you find is that it's indeed the same structure. You find that there's an epsilon term and an epsilon square term, just like in the field theory calculation. And when you compare all the parameters, you find that this coupling T takes this particular value, which is actually in agreement with the value you need when you compare the perturbative string formula to what you get in the field theory. So that's basically where we are in terms of actual results. And there's I mean, we're in the process of doing some of those things mentioned here. So, there's a lot of things that were not done in this TT bar deformed CFT. Like, for example, on the understanding the symmetries of this theory. You know, before you turned on the deformation, obviously you had a Virasoro symmetry, and there's a feeling that after the deformation, there's still some large symmetry that governs this exact solvability. This is not really understood. These two papers last summer talked about the spectrum. You can do correlation functions, but this hasn't been done. And there are some reasons to believe that if you look at the UV limit of this theory, there's interesting things happening. Essentially, you recover some kind of diffeomorphism invariance. I think this might be related to some things that were said here earlier. And since I'm now at 0, I will not go over this, but basically the message is that most of the things that you would like to know about this theory, we don't know yet. They remain to be understood. So, I'll stop here.
Thank you very much. Questions?
So I have a question about correlation functions because, well, as I was trying to explain yesterday, a rigorous way to define the bar deformation in 2 dimensions is really in terms of S-matrix dressing.
Wait, I can't really hear you very well. Say it again?
So I have the question about correlation functions
that
here.
part I heard.
Yeah, so yesterday I was trying to explain that the rigorous way to define TT-bar deformation is in terms of S-matrix dressing.
Define what information?
TT-bar deformation.
Oh, TT-bar deformation.
That corresponds to this S-matrix dressing, which I was talking about yesterday.
Yes.
And it's really a theory of gravity. It's a theory of Jacques-Teitelbaum gravity. So one doesn't expect to find correlation functions in this theory because it's gravitational theory.
So here is what I know. So here is what I know about this. So you can ask the question, if you start with a local correlation function in the original CFT, you take some operator O of x, and you start with some, say, 2-point function, O of x, O of y, then you ask what happens to it under this TT-bar deformation, just in the field theory. So I think you can convince yourself easily, and from the holographic point of view, it's very obvious that this object doesn't exist, really. The object that does exist is if you Fourier transform this 2-point function to momentum space, then you can deform, and the correlation function in momentum space does exist, but it cannot be Fourier transformed back to position space. I didn't have time to talk about this here, but I believe that statement is true. Now, regarding this gravity that you were mentioning in your talk, it's not really understood, but I think that what probably is going on here is the following. If you do this Hubbard-Stratanovich, whatever trick, and you split this TT-bar with some auxiliary thing, which in this case will be a metric rather than a scalar field, then you can convince yourself that in the UV limit, where formally this thing I called little t goes to infinity, the theory recovers some kind of diffeomorphism symmetry. And I believe that that might be the place where this thing comes in, this gravity. So the point is that this diffeomorphism invariance is somehow not a property of the theory at all scales. After all, in the infrared, you go to the CFT, which is not diffeomorphism invariant. And so I think it's probably true that in the UV, things become much simpler, as I mentioned here. But it's not understood. So I understand what you're saying, but the short answer is that it's not really understood, but there's a lot to say. And actually, the string theory construction sheds a lot of light on these correlation functions. Like this Coset description is one in which you can just calculate things, and we're in the process of doing that.
Okay, one last quick question.
So, one naive confusion.
I really can't hear you.
One confusion I have, which perhaps this analysis would shed light on, is boundary conditions for gravitons in general AdS spacetimes don't admit double trace, don't allow for double trace deformations. Just like And so, is there something that one can learn from this analysis for what's special about this particular story in
that's
AdS?
actually, there is an interesting story there, which actually Massimo Porratti explained to me. So I don't know what you mean when you say what you said, but one thing that is true is that if you try, like you read the papers by some people in the audience about double trace deformations and you try to implement them in this case, you find in general some singularities. Is that what you meant? Okay. So, but what you also find is that, let me just, instead of talking a lot about something, this is actually an interesting point that, as I said, Porratti explained to me. So, the situation is like this. If you take your deformation to be, say, something like this, where instead of the minus sign, you have plus alpha with arbitrary alpha, what you say will happen. But if you set this alpha to be precisely equal to -1, it will not. Okay, so that's what you learn, if you want, from the fact that this theory makes sense with the double trace deformation, which again is not something we studied here.
Okay, I think we should move on.